First, I would like to briefly introduce our topic of selection, which is electron microscope in geology and earth science. Electron microscopes are advanced instruments that use a beam of electrons instead of visible light to produce highly detailed images. Because electrons have so much shorter wavelength than light, electron microscopes can achieve much higher resolution and magnification. In geology and earth sciences, they are widely used to study minerals, rocks, soils, and fossils, helping scientists to understand the composition and structure of earth materials. Next, there are a few significance of electron microscope in geology and earth sciences that we can acknowledge. First, electron microscope can provide extremely high magnification and resolution for observing microscopic geological features. Second, they enable detailed analysis of mineral composition and structures. Third, they can assist in the investigation of fossils and ancient biological remains. And last but not least, they aid research in volcanology, sedimentology, petrology, and planetary geology.
Now, I will explain why electron microscope is relevant as a scientist instrument. Electron microscopy is an important scientific instrument because it allows scientists to observe structure at the microscopic and nanoscopic scale that cannot be seen using conventional optical microscope. Its high-resolution imaging capability enables researchers to study materials in great detail and obtain accurate information about their structure and composition. In addition, electron microscope can be used for elemental analysis, helping scientists identify the element present in a sample. Because of these capabilities, electron microscopes are widely used in scientific research, particularly in geology and earth science, where they have researchers examine minerals, rocks, and other geological materials. Therefore, electron microscopy is a powerful and essential tool for advancing scientific understanding and investigation. Next, I will explain the two main types of electron microscope, which is the transmission electron microscope or TEM and scanning electron microscope or SEM. First, the transmission electron microscope or TEM works passing a beam of electron through an extremely thin example. The electron travels through the specimen and create an image that reveals the internal structure of the material. Because of its high resolution, TEM is useful for studying very fine detail inside a sample. The second type is the scanning electron microscope or SEM. Unlike TEM, SEM scans a beam of electron across the surface of a sample. This produces highly detailed image with three-dimensional appearance, allowing researchers to observe surface features clearly. In earth science and geology, SEM is the most commonly used type of electron microscope. This is because it provides excellent image of mineral surface, rock texture, and microstructure, helping scientists better understand the composition and formation geological materials. Therefore, both TEM and SEM are important tools, but SEM is generally more suitable for examining geological samples due to its ability to produce detailed surface image. Now, let's move on to the main component of an electron microscope and their function. The first component is the electron gun, which generates and emits a beam of electron. This beam acts as the source of illumination for the microscope. The second one is electromagnetic lenses. These lenses use magnetic field to focus and control the electron beam, similar to how glass lenses focus light in an optical microscope. Next, the vacuum chamber is another important component. It maintains the vacuum environment inside the microscope, preventing electrons from colliding with air molecules, which could affect image quality. Next, the sample stage is used to hold and position the specimen during observation. It allows the sample to be adjusted so that a specific area can be examined in detail. The detector collects signal produced when the electron beam interacts with the sample. This signal contains information about the sample structure and composition. Finally, the display and computer system process the collected signals and convert them into a high-resolution image that can be viewed and analyzed by the researcher. Together, these components enable electron microscope to produce detailed image and provide valuable information for scientists' research, including studies in geology and earth science. Now, let's look at how an electron microscope works. The process begins with the electron gun, which emits a beam of electrons. These electrons are then accelerated to high speed by the anode. Next, condenser lenses focus the electrons into a narrow and precise beam. The beam travels through a vacuum chamber to prevent collision with air molecules, ensuring clear and accurate imaging. The focused electron beam then researches the sample. In a scanning electron microscope or SEM, the beam scans across the surface of the specimen. As the electrons interact with the sample, different signals are produced, including secondary electrons and backscattered electrons. These signals contain information about the sample surface feature and composition. The detector collects these signals and converts them into electrical signals. Finally, a computer processes the data and generates a high-resolution image that can be analyzed by researchers. This process allows electron microscope to reveal microscopic details that cannot be observed using conventional optical microscope.
Next, I will explain about detailed exploration of electron microscope in earth science and real-world implementation. First, electron microscope play an important role in geology and earth science because they provide extremely high magnification and resolution compared to optical microscope. This allows scientists to observe the microstructure, composition, and morphology of geological materials in great detail. One of the main applications of electron microscope in earth science is minerals identification and characterization. Using a scanning electron microscope, which is SEM, researchers can examine the surface features of minerals, determine the grain size, and identify mineral species that are too small to be observed using conventional microscope. This information is essential for understanding the formation and evolution of rocks. Electron microscopes are also widely used in the study of rocks and soil. Because scientists can analyze the texture, porosity, and chemical composition of rock sample to investigate geological processes such as weathering, erosion, and sedimentation. In addition, SEM combined with energy dispersive X-ray spectroscopy, which is EDS, that enables elemental analysis and allowing researchers to determine the chemical elements present in geological specimens. Next, we go to our second category, data exploration of electron microscope in real-world application. In real-world application, electron microscope is used in mining and mineral exploration industries. Geological samples that have been collected during the exploration are analyzed to identify economically valuable minerals and evaluate their quality. The technology is also used in environmental studies to investigate soil contamination, airborne particles, volcanic ash, and other geological hazards.
Moving on to the potential benefits, utilizing electron microscopy in geology and earth science provides several critical breakthroughs that traditional petrographic methods simply cannot match. We can categorize this into three primary pillars of benefits, which is sub-nanometer resolution, sample preservation, and dual capabilities. First, let's discuss about sub-nanometer resolution. In conventional geology labs, standard optical polarizing microscopes are fundamentally restricted by the physics of light wavelengths, meaning anything smaller than 200 nanometers becomes a blur. Electron microscope overcome these physical limits entirely by using accelerated electron beams instead of light. This allows geologists to easily view nanoscale features with rock formations. Our second major benefit is its capacity for non-destructive testing, or we call as NDT. In earth science, we are frequently tasked with analyzing exceptionally rare, pristine, or entirely irreplaceable geological specimens. Think of lunar soil sample, meteorites, or deeply sourced mantle sonolith brought up from the Earth's core. we cannot afford to destroy them. So it is because electron imaging interacts with the sample surface via electron scattering. It allows us to capture high definition, high magnification morphology without altering the fundamental physical or structural integrity of these precious materials. For the third benefit is dual capabilities. It doesn't just show up. It doesn't just show us a pretty high resolution picture. It is also simultaneously decodes the chemistry by integrating energy dispersive X-ray spectroscopy, widely known as EDS detectors. The system analyzes the characteristic X-ray emitted by the sample when hit by the electron beam. This means that as a geologist, you can simultaneously analyze the complex 3D surface topography of a crystal and map out its exact elemental composition in a real time, differentiate between complex solid solution mineral intensely. However, despite these amazing potential benefits, operating an electron microscope in geological research comes with a real technical and operational challenges. So, the first major challenge is the sample charging effect. Because most rocks and minerals are electrical insulators, so they don't conduct electricity well. When hit by the high energy electron beam, negative charge build up on the sample surface, which distorts the final image. To fix this, we have to go through complex sample preparation. This requires a slow, meticulous process that including slicing the rocks into thin sections, polishing them completely flat, and spatter coating them with an ultra thin layer of carbon or gold to make them conductive. Lastly, there are high operational costs. These are extremely expensive instruments with high ongoing maintenance fees. Furthermore, they require highly specialized clean room facilities to isolate them from vibration and magnetic interference. So, to overcome this exact limitation, the field of microscopy is evolving rapidly. Let's look at the future innovations transforming Earth science. The first big innovation is environmental SEM. Unlike traditional vacuums, ESEM allows us to image wet, oily or completely uncoated rock samples in their natural unaltered state without destroying them. Next is AI and machine learning integration. By using a smart software, the system can automatically map mineral grains, identify crystal types, and detect microfractures instantly, saving researchers hours of manual labor. Finally, we are seeing miniaturization through desktop SEM. Electron microscopes are shifting from room-sized installations into portable compact desktop units. This allows geologists to run high technology on site, analyze directly out mining field or active volcanic research stations.
Based on our discussions, we can conclude electron microscopes are powerful tools that provide highly detailed images of Earth materials through the use of electron beams with short wavelengths. Their advanced imaging and analytical abilities have greatly improved the study of minerals, rocks, soils, and fossils. Despite challenges such as high cost and complex operation, Ongoing technological developments continue to enhance their application in geology and earth sciences, making them essential instruments for future research and innovation.